Equilibria for weak acids and bases. We're going to learn how to calculate the pH for a weak acid or weak base solution in this lesson. In the last chapter on acids and bases, we learned how to calculate the pH for a strong acid or base, and we could do that because they dissociate 100%. Those reactions go to completion. But for a weak acid or base, they only dissociate to a small extent and reach some sort of intermittent equilibrium. Well, because we hadn't covered equilibrium yet, we didn't know how to calculate pH for them. That's what we're going to learn in this lesson. It turns out there's a characteristic of what we call Ka or Kb, which are equilibrium constants for weak acids or weak bases respectively, that will allow us to do such calculations. Now, this lesson is part of my high school chemistry playlist. I'm releasing them weekly throughout the school year, so if you want to be notified every time I post a new lesson, subscribe to the channel and click the bell notification. All right, so we're going to start with weak acids. And generically, we can write any weak acid as being represented by HA. So whether I write HF, where A here would be the F, or HC2H3O2, that's acetic acid, the A here would be the C2H3O2, or HCN, the A would be CN. So any weak acid can be represented by the formula HA. So that's our generic weak acid. And in this case, your Ka expression is the equilibrium constant for when HA dissociates in water. And so in this case, what it dissociates in water, so this is going to act as a Bronsted-Lowry acid and donate H plus to water, which is going to give you H3O plus. So, and then you're going to be left after he donates the H plus, he's going to be left as his conjugate base, which is A minus. And so your Ka expression is the equilibrium constant expression for just such a reaction. And so in this case, generically, we can write this like so, and this is just products over reactants, H3O plus times A minus over HA. And you might be like, well, Chad, what happened to the water? Well, you might recall that if for equilibrium constant expressions, and again, a Ka is just another type of equilibrium, or a special type of equilibrium constant expression, but no solids or liquids typically. Now, every once in a blue moon, you actually can see a liquid if it's not the solvent in the reaction. But here, water, this is an aqueous reaction, aqueous, aqueous, aqueous. Water is totally solvent. And when your liquid, when your solvent shows up in a reaction as a liquid, it is not going to show up in the equilibrium constant expression. So typically no solids or liquids. All right. So you could be asked for the Ka expression for any given acid or base. This is the generic one. But if I said, hey, what's the Ka expression for HF? Well, then it would be H3O plus times F minus all over HF. And you would just plug in your specific acid and its specific conjugate base into such an expression. Now, one thing to note for a weak acid, so sometimes we leave the water out of the equation entirely and just come up with an equivalent expression here. And we just say HA dissociates to give H plus and A minus. And this is completely equivalent. You might recall that we said that H plus and H3O plus, back in the acid base chapter, we said that these should be treated as equivalent. Now we said that H plus, which are naked protons, probably don't exist to any appreciable amount in water, and they combine with water to form H3O plus, which is why it's probably more proper to write it like this, but you'll see both used, both in textbooks and by instructors alike. And so you might also see this Ka expression written instead as H plus times A minus all over HA. And so you should definitely treat these as equivalent. You might see either one. And so again, if you were asked a question on a test or quiz that said, write the Ka expression for HF, you could write it as H plus times F minus over HF, or H3O plus times F minus over HF. Either would be correct. And if it was a multiple choice question, either one of those could be the correct answer. Obviously, only one of them should show up then. All right, so there's the first part here. We got this lovely Ka expression, and you should be able to write that for any acid. Here we've, again, generically written the equation, the chemical reaction, as well as the Ka expression. So generically, but again, you should be able to do it both generically, but also for any specific acid if provided. Okay, so the whole goal here oftentimes is to calculate a pH. It doesn't have to be the goal, it just often is. And the key there is figuring out how much H3O plus we have present at equilibrium. That's going to be the goal. Well, it turns out we said that weak acids only dissociate to a small extent, usually less than 5%. So let's just say we had, 0.1 molar H, let's get this right, C2H3O2. Let's just say we had that. So if we had 0.1 molar C2H3O2, which is going to be my example of HA here, the question is how much H3O plus would we get? Well, it's not going to dissociate completely, so we're not going to get 0.1 molar H3O plus, but it turns out it's not even probably going to dissociate 5%. It's going to be less than that. And so it's not even going to be 5% of 0.1 molar. Well, what percent is it going to be? Well, it depends. It depends on what equilibrium constant we have for HC2H3O2, it turns out. So, and it also depends on the concentration. So it would be nice if actually acetic acid here, C2H3O2, dissociated the exact same percentage every time. It just turns out it doesn't. Like if I told you it dissociates 1%, well then you just take 1% of 0.1 and that'd be your concentration of H3O plus. So, and the problem is that percentage varies depending on the concentration of your acetic acid. It turns out the greater your acetic acid concentration, the lower the percent it dissociates. And so that's why we're not giving you percent dissociations, because they're not constant, but the equilibrium constants are constant, again, for a given temperature. And so that's why we got to use these, which is a little more tedious than just having a set percent dissociation, because those aren't set. All right, so it turns out these Ka values are a measure of acid strength as well. And notice these Ka values are all small. 6.8 times 10 to the minus 4, that's 0.00068. Set 1.76 times 10 to the minus 5, that's 0.0000176. 4.9 times 10 to the negative 10, that's 0.9 zeros and 49. So really small numbers. And if you recall an equilibrium constant, when it's a really small number, smaller than 10 to the negative 3, smaller than 0.001, that tells you it's going to be a reaction that favors the reactants at equilibrium. So these don't dissociate to a very large extent. They're not going to produce a lot of products. They're going to favor having a lot of reactants present at equilibrium. So that's the first thing. And so for your weak acids, we typically see very small numbers like this. That's pretty typical. So, but the goal though is that based on how small they are relative to each other, you can actually rank the acids. So it turns out we rank acids, we talk about their strength based on the degree to which they dissociate. If you recall, we called the strong acids the one that dissociated 100% all the way. Well, it turns out for the weak acids, we can talk about which ones are stronger and weaker. And if you have Ka values, that's a great way to tell. And it turns out the larger the Ka value, well, then the more it's going to dissociate to form products. And the more it dissociates to form products, the more H3O plus you form, the stronger the acid. And so it turns out we can come up with a relationship here. So the higher the Ka value, the stronger the acid. So higher Ka, stronger acid. So if I gave you these three acids and I said, hey, which one is the strongest acid? Well, the largest of these three is 6.8 times 10 to the minus 4. So HF would be the strongest of those three acids. Okay, but it turns out there's one other thing you can get as well. So it turns out there's a rule, and we'll kind of derive a mathematical basis for it in a little bit. So, but it turns out the stronger an acid, the weaker its conjugate base. And so here I can compare these three acids directly using those Ka values. But I could also ask you to compare their conjugate base. I could give you F minus, C2H3O2 minus, and Cn minus, and say which one of these is the strongest base. Well, if I want to know which one of these is the strongest base, and I don't have Kb values for them, like we'll talk about in a little bit, so, and that's often common for ions not to have the equilibrium constant values, but I do have the Ka values for their conjugate acids. And so if I want to know which of these bases is the strongest base, well, the strongest base would be associated with the weakest conjugate acid. And so I'd look up at this table and be like, oh, 4.9 times 10 to the minus 10. That is the smallest of these three Ka values by far. HCN is the weakest of these three acids, and if he's the weakest acid, then Cn minus, his conjugate base, would be the strongest of the three conjugate bases. So that's where that also could come up in a question as well. So again, if you're given Kas, not only does that allow you to rank acid strengths, but you can rank the base strengths of the conjugate bases in the exact reverse order. So that's for our weak acid. Now I also want to deal with weak bases for a second here. And in this case, when we write the equilibrium for weak base, we often use the conjugate base when introducing this. We could also use the letter B, and I'll do that as well. So, but I'm going to introduce it just like so, and the base I'm going to introduce this with is the conjugate base of the generic acid we used just a minute ago. And so when we're dealing with a base instead of an acid, once again, just like we have a Ka for acids, we're going to have Kb's for bases, and a Ka describes an acid dissociating in water, reacting with water. A Kb is going to describe a base dissociating water, reacting with water. So an A minus here is going to act as a Bronsted-Lowry base. It's going to be a proton acceptor. It's going to accept a proton from H2O. And if we steal a proton from H2O, he's the acid, we're going to be left with OH minus this time. And then the conjugate acid. So when he accepts the H plus, he becomes HA. All right, so this is the generic Kb chemical reaction. And now we can come up with a Kb expression as well. And again, it's just products over reactants. It's just an equilibrium constant. So it looks like so. Now, one thing to note about this is I said also sometimes you'll see this written generically with just B for base, and that'll be just a neutral base. In which case, then, we're still going to form some hydroxide here after we take the H plus away from water, but when he gains an H plus, he not only gains an H, but he gains the plus charge as well. And so you might see it written like so. And so you might also see this written and represented as OH minus times BH plus all over B. And so you could see that represented either way, just as an FYI as well. Cool, there's one advantage to representing it the first way. So because there's a nice relationship we can derive. So when dealing with the Ka of an acid and the Kb of not just any base, but its conjugate base. So if HA and A minus really are a conjugate acid, conjugate base pair, then if I look at their Ka, Kb expressions, we can derive something very useful. And that useful expression is that Ka times Kb equals Kw. So and we dealt with Kw in the last chapter, and it was a value of 1 times 10 to the negative 14. It's the auto-ionization constant for water. And so when water dissociates, it just forms H plus and OH minus. So and it turns out the Kw expression is therefore going to equal that. So let's take a look at that auto-ionization of water. And so we had water dissociating to give, let's get this right, H3O plus and OH minus. And the equilibrium constant for this auto-ionization was called Kw. And again, we saw this in the acid-base chapter. Now, it turns out if you take the Ka expression, so H3O plus times A minus over HA, and multiply it by the Kb expression, OH minus times HA all over A minus, you'll find that a lot of these things cancel. So if you notice, like your A minus would cancel when you multiply these expressions together. Your HA numerator, or denominator here, numerator here, it's going to cancel as well. And all you're going to be left with is H3O plus times OH minus, which is the same thing as the Kw. So Kw here simply equals H3O plus times OH minus, and because the reactant is the liquid solvent, it doesn't show up in the expression. So it'd be products over reactants, and when none of your reactants show up in the expression, it's just over 1, which is just the same thing that it is. So it's just H3O plus times OH minus for Kw. And again, if you take the Ka expression times Kb, it simply equals H3O plus times OH minus, which is Kw. And so that's where this comes from. And so notice Kw is just a constant. It's 1.0 times 10 to the negative 14 at 25 degrees Celsius, room temperature. But what we see here, and again, this is only true when you have an acid and its conjugate base. Not just any acid base, but an acid with its conjugate base. So that the stronger an acid is, well, then the weaker its conjugate base must be. So just like a higher Ka means a stronger acid, a higher Kb would mean a stronger base as well. Well, because these multiply to give you the same exact constant, if your acid goes up and gets a higher Ka value, by necessity, its conjugate base would have to have a smaller Kb and therefore be a weaker base. And so this is the mathematical basis for what we said earlier, where the stronger the acid, the weaker the conjugate base. Cool. So that's a big takeaway here. And pretty much from here, we are ready to do some pH calculations. Let's make some room. All right, so we've got 3 calculations to do for weak acid bases, and we'll start with weak acids. And the question is, what is the pH of a 0.1 molar solution of acetic acid? And the Ka for acetic acid is given. Now, we had the formula for acetic acid on the board a little bit ago, but even if you don't have the formula, you can always just use the generic reaction and the generic Ka expression for any weak acid when you're doing calculations. So even if you don't know that acetic acid's HC2H3O2, doesn't matter. We can just use the generic for performing the calculations. Now, in this case, we're told it's a 0.1 molar solution, and so the real question is going to be, to get the pH, how much H3O plus is present in that solution, and it's going to come to some intermittent equilibrium, and a useful tool for figuring out the amount of H3O plus present in equilibrium will be this ice table we learned about in the last lesson. And so in this case, the initial concentration of HA before it dissociates is 0.1 molar. Before it dissociates, we really shouldn't have any significant amount of H3O plus or A minus in that solution. And so in this case then, your change is going to be minus X here, plus X here, plus X here. It's a 1-to-1-to-1 ratio. So subtracting on the reactant side, gaining it on the product side, and then initial plus change gets you your value at equilibrium. So this is just going to be 0.1 minus X. This will be X, and this will be X. And now we know our equilibrium concentrations of all three species in terms of a single variable X, and we can now plug it into our expression. So the Ka value is, again, that 1.76 times 10 to the negative 5, and that's going to equal the concentration of H3O plus, which is X, times the concentration of A minus, which is also X, all over the concentration of HA, which is 0.1 minus X. And so here we've got our first major issue here, and the major issue is that if you actually solve this for X, the most mathematically accurate way of solving for this is going to involve a quadratic expression, because you're going to have X times X, which is X squared. You're going to have an X squared term and an X down here, and you'd have to multiply this up to the other side, combine all the terms onto one side, and then you'd have to solve a quadratic. And again, highly unlikely you're ever going to need to solve a quadratic in a high school class. So that's the first part. But we'd never do it in the context of a weak acid anyways, at almost any level, until you start reaching kind of, high undergrad level stuff. So the way we get around it in this case is by taking into account that 1.76 times 10 to the negative 5 is a small number. And when you have an equilibrium constant that's a small number, again, that's a reaction that's going to favor the reactants. And so in this case, we start off, if you look at our initial concentration, we start off with only reactants. And when this reaches equilibrium, based on the equilibrium constant value, I can say that we'd have mostly reactants. And so if you start off with only reactants, and then when the reaction reaches equilibrium, you still have mostly only reactants, well, that tells you that the amount that reacted, X, must be small. So, and the key is, when you add or subtract a small number, it doesn't affect much. So if I told you, hey, you know what, I'm moving, and I'm leaving the United States, and I'm moving to Australia. Well, there's, 329 million people living in the United States. Are they going to feel the need to take a new census after I leave to figure out the new population because I left? No, and what we learned here is that I'm insignificant. So if I leave, the population doesn't largely change, because we're adding, or in this case subtracting, a number so small compared to the number you're subtracting it from. Same thing, when I get to Australia, they're not going to feel the need to take a new census either, and I'm still insignificant in Australia. So adding, again, a small number, just one of me, to, the 50, 60, 80, I don't know how many people live in Australia. However many millions live there, though, I'm still going to be insignificant. And so when you add or subtract a small number from a much larger number, it doesn't really affect much. And so same thing here, when you take 0.1 minus a really small number, and again, we know it's small because the equilibrium constant is small. So essentially, that's not going to matter much. Just don't worry about it right there. Now, if you multiply or divide by a small number, that has a huge impact mathematically. So you can't ignore like these. These are multiplied together. You can't ignore those x's. It's only when it's added or subtracted, when you have a very small equilibrium constant like we do here, that we can ignore it. And what's nice by ignoring it, it makes the math so much easier. So x times x is x squared. And then instead of 0.1 minus x, it's now just 0.1, because 0.1 minus a really tiny number is still, for all intents and purposes, 0.1. Hasn't really changed it much at all. Now, it might be like 0.09999, something like that, but it's, for all intents and purposes, it's practically going to be still 0.1. Cool. So we'll just multiply up by 0.1 on that side, and we'll get x squared equals 1.76 times 10 to the negative 6, which happened when you multiply by 0.1. And then we'll just take the square root of both sides to solve for x. And this we'll definitely use a calculator for. So we'll take the square root of 1. And I said 76. Yeah, 76 times 10 to the negative 6. Oh, let's get that right. 10 to the negative 6 equals 0.0013, or 1.3 times 10 to the negative 3. That's going to be in units of molarity. And we can also confirm that this was small enough to ignore, because again, this really would have been, in the denominator, 0.1 minus, well, let's write it out, 0.0013. And so the question is, were we good in just ignoring that minus 0.0013 that would have been in the denominator? Well, the key is this: as long as the number you're subtracting is less than about 5%, that's kind of the rule of thumb. As long as it's less than 5% of the number you're adding or subtracting it to or from, good call. So it will be statistically insignificant in that case. Well, in this case, 0.0013 is actually 1.3% of 0.1. If you take 0.0013 divided by 0.1 times 100, you get 1.3%. That's less than 5%. Ignoring it here, again, good idea. Cool. And so here x is 1.3 times 10 to the negative 3 molar. And it turns out that's what I wanted. I really just wanted whatever goes in this box. I want the equilibrium concentration of H3O plus, and it just happens to be x. And so what we've learned here is that at equilibrium, the H3O plus in this solution will be that 1.3 times 10 to the negative 3 molar. And don't forget that pH is negative log of your H plus or H3O plus, same diff. And so in this case, we'll take the negative log of 1.3 times 10 to the negative 3 to get our pH. So negative log, and I'll actually take it of the entire number in my calculator, 0.0013266 and some change. So negative log of that answer is going to get us 2.877, and I'll round that to 2.9. Cool, so we've done our first pH calculation with a weak acid, and it was kind of a doozy. Like, this kind of sucks. It was so much easier for a strong acid. For a strong acid, if you had 0.1 molar HCl, you'd just be like, well, it dissociates completely. So you get 0.1 molar H3O plus, and negative log of 0.1 is 1, and you're done. It sucks so much more for a weak acid with having to factor in that it reaches some sort of intermediate equilibrium. However, now we're going to cheat. So let's go back a step here real quick and go right back here. So because we're always going to ignore this little minus x for the weak acids we're going to see in a high school course, it actually allows us to come up with a nice simple formula for calculating the H3O plus concentration. And so in this case, we can come up with, and actually I shouldn't have erased this Ka expression. Let's get that back. H3O plus times A minus over HA. All right, so if we look at that here for a second, so for our HA concentration, again, this is the concentration at equilibrium, but if we always ignore the minus x, then we're actually just taking and making that essentially the same as the initial concentration as well. So we're just saying, the initial concentration, the equilibrium concentration, they're about the same. Okay, well, if we do that, we can come up with an expression here. So we'll take and multiply that by the other side here. We'll have Ka times the initial concentration of HA equals H3O plus times A minus. But notice the H3O plus and A minus concentrations were both equal to x. And so in this case, we'll just say x squared, and then we'll take the square root of both sides. So in this case, x is going to equal the square root of Ka times your initial acid concentration. That's how we'd solve for x in the ice chart. Except the whole point of this whole ice chart, if we're trying to do a pH calculation, it wasn't really to get x, but to get the H3O plus concentration, which just happens to equal x according to our ice chart here. And so in this case, that is the H3O plus concentration. And we've now come up with a very simple expression for calculating the H3O plus. Can you still use this ice chart? Yes. Will you get the right answer if you do? Yes. Will it take longer? Yes. Should you know how to do this anyways? Yes. So that's why I took the time to go through the whole thing before giving you this nice, easy little expression. So, but notice if we just use this lovely little expression, we say, okay, Ka was 1.76 times 10 to the negative 5 multiplied by the initial HA concentration, which was 0.1. So times 0.1, and that gets me the 1.76 times 10 to the negative 6. And then we'll take the square root of it all. So square root of that last answer, and we get, lo and behold, the exact same answer. And notice it's exactly the same math that we did before. Cool. So for weak acids and bases, it technically is an ice chart kind of situation if you're doing a pH calculation. But based on how we solve them, though, with ignoring that minus x, you can actually treat it by just using the simple formula. Ka times the acid concentration, take the square root. gets you your H3O plus, and then you can take the negative log from there. Cool. We'll see it works similar for weak bases in a little bit, but before we get there, we got one more weak acid problem to take into account. All right, in this next problem, we got what is the Ka of a weak acid, HA, if the pH of a 0.1 molar solution is 3. So we're told that the concentration of our acid initially is 0.1 molar, and that the pH is 3. So this one we're going backwards. Instead of being given a Ka and asked to find the pH, now we're given the pH and asked to go back and find the Ka. And we'll work this a little bit backwards. Now, one thing you should keep in mind, if the pH is 3, what this means is that your H3O plus concentration is 10 to the negative 3. So recall that H3O plus is 10 to the negative of whatever your pH is. If your pH is 3, well, that's 10 to the negative 3 molar, which is the same thing as 1 times 10 to the negative 3 molar in this case. All right, so we know our H3O plus. That's going to be helpful in setting up our ice table. So in this case, if we set up our ice table, initial concentration here is 0.1, 0, 0, minus x, plus x, plus x, 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 0.1 minus x. But the key here is that we actually know x. Because we know we're given the pH, we know the H3O plus is 10 to the negative 3. Well, that's what goes in this box right here. And so instead of x, we could have actually filled that in as simply 10 to the negative 3, or 1 times 10 to the negative 3, 0.001. Well, but that's what x is. So then this is also equal to 10 to the negative 3 molar. And this one over here, 0.1 minus x, is 0.1 minus 10 to the negative 3. And now we can calculate what that is, but we know all three equilibrium concentrations. Notice 0.1 times 10 to the negative 3. Let's work that out. So 0.1 minus 0.001 is 0.099. Cool, and we could just plug those into our Ka expression to get the equilibrium constant. So in this case, Ka is going to equal 10 to the negative 3 times the A minus, which is 10 to the negative 3, all over the HA concentration of 0.099. Now you might be like, hey, Chad, you know, in the last example, we ignored the minus x part of it. So why aren't we doing that here? Because we don't have to. The reason we did it last time is because it allowed us to avoid the quadratic, which was a huge mathematical bonus by not having to do a quadratic. But here, whether I include it or not, I don't have to do a quadratic. And so will it affect my answer much? Probably not. But I can get a more accurate answer, and I still don't have to do a quadratic, so I might as well. And so in this case, we'll take 10 to the negative 3 squared divided by 0.099, and we get 1.01 times 10 to the negative 8. We probably round that to 1.0 times 10 to the minus 8, but that's our Ka value having been given the pH. So again, you could see this either way. You could be given the Ka and asked for the pH, or you could be given the pH and then asked to go get the Ka, and that's why I worked an example of both. Let's take a look at a weak base calculation real quick. All right, in this last problem, we're asked, what is the pH of a 0.1 molar solution of ammonia? And then in parentheses, we're told that Kb equals 1.75 times 10 to the negative 5. So that must be the Kb of ammonia. So in this case, again, weak base number that is smaller than 0.001, the reaction is going to favor the reactants at equilibrium. And even if you don't remember that the formula of ammonia, which was not given in the question, is NH3, so you could still do this. Now, if you set it up with NH3, you could, instead of using the generic Kb chemical reaction, you could actually plug in ammonia and do NH3 aqueous plus water. Still gives you hydroxide plus the conjugate acid of NH4 plus after he gains an H plus. And you could get a specific Kb expression as well. OH minus, and instead of just HA, now we're going to have the actual conjugate acid of NH4 plus. And then all over, instead of A minus, it's the actual base of NH3. And again, that's a question you could be asked, right? You could be asked to either come up with what's the Kb reaction for ammonia, NH3, they'd give you the formula typically, or what's the Kb expression, as well. And you could be asked to write those. So, but whether we actually write them or not, we can do the calculation without having to write any specific Kb reaction or Kb expression. We could just use the generic ones as well. All right, so in this case, if we set up our ice chart again, initial concentration of ammonia was 0.1 molar. So these would both be zeros. And again, we don't care about water because he's not going to show up in our expression being a liquid. And we'd have minus x plus x plus x. 0.1 plus a negative x is 0.1 minus x. 0 plus x is x, and 0 plus x is x. And so now we've got our equilibrium concentrations all in terms of a single variable, and we would just, again, plug them into our Kb expression. And so here we'd end up with Kb of 1.75 times 10 to the negative 5 equals x times x, or x squared, all over 0.1 minus x. And this should look really similar to what we did just a second ago. And the reason it looks so similar is, one, I chose a base whose Kb was really similar to the acid's Ka we used in the first example. But also I used a 0.1 molar concentration of a base, just like I used a 0.1 molar concentration of that acid. And so the equation here looks remarkably similar. And in the same sense, we know x is going to be small because our equilibrium constant is small, and 0.1 minus a small number is essentially 0.1. And so we'll multiply it by 0.1 and take the square root and go from there. And I'll take this moment just to say that we have a similar shortcut to the way we did for a weak acid. So, but with a weak base, you're not solving for the H3O+, you're solving for the hydroxide concentration. And in this case, instead of being the square root of Ka, it's the square root of Kb. And instead of being Ka times the acid concentration, it's Kb times the initial base concentration. I'll actually write it as B. So if I write an A minus there, a lot of students see the A and they're like, A for acid? Well, not technically. So, but B for base, they're good with that. And so I'll write it like this. And so notice when we solve this, we're going to multiply it by 0.1. And so we're going to have x squared equals 1.75 times 10 to the negative 5 times 0.1. And then we'll take the square root of both sides. And notice that's exactly what we get right here. We'd have the 1.75 times 10 to the negative 5 times the 0.1, taking the square root. And so it leads us to exactly the same place. So I derived it with the ice chart, but again, we have a nice, lovely shortcut for doing pH calculations with weak bases. The key you have to remember is that you're not solving for H3O+ with a base. Bases dissociate to produce hydroxide instead. And so we'll have one extra step in our calculation here. So let's take a look here. So if we take 1.75 times 10 to the negative 5 times 0.1 should give us 1.75 times 10 to the negative 6. And then we'll take the square root. And we get 1.3 times 10 to the negative 3. I should have realized we're exact same calculation essentially we did before. And that's in molarity. And in this case, again, that equals the hydroxide concentration, not the hydronium concentration. And if that equals hydroxide concentration, then when I take the negative log, I don't get the pH, I get the POH, and then we'll subtract from 14 to go there. And so in this case, if I take the negative log of 1.3 times 10 to the negative 3, we already learned that that's going to give me 2.9, but that's a POH. And when I subtract from 14, I get a pH of, in this case, 11.1. Cool, so real similar setup to what we saw for weak acids, but one extra step at the end because we end up calculating a POH instead of the pH, and then have to subtract from 14. Now, if you found this lesson helpful, would you consider giving me a like and a share? The best thing you can do to make sure other students get to see this lesson as well. If you are looking for practice problems, if you're looking for the study guides that go with these lessons, check out my premium course on chadsprep.com.